A very good morning, students. Now we are going to see the next thing, that is the behavior of conductors in an external field. Till now we were dealing with the derivations on the mathematical part in physics, but now we are going to learn the physics in a little different way. So let's start with the first thing, that is how the conductors behave when they are kept in an external field. As you can see in this figure, there is a conductor which is placed in an external field, and the direction of electron field is from positive to negative, because we know that for positive charge the field acts radially outwards. So when the conductor is placed in this field, since it is an uncharged conductor, so it will have equal number of positive and negative charges in it, and the negative charges will get induced on the left side due to these positive charges. Same way, the positive charges of the conductor will get induced on the right side. These positive charges will get induced on the right side, and due to the accumulation of charges, internal field or the induced field will get set up inside the conductor, which is denoted by EIND, that is induced electric field. And the accumulation of charges will take place till the external electric field is becoming equal to the internal field. It means the net field inside the conductor is 0. So this is the first thing about conductor, that when it is placed in an external field, then there will be no field inside the conductor, or the net field inside the conductor would be 0. Now we are going to see the next thing. The second is, just outside the surface of a charged conductor, electric field is normal to the surface. Means, for example, this is a surface, this is any conductor, then on the surface of the conductor the electric field will be pointing normal to the surface. How can we say that it will be normal to the surface? Suppose it is not normal to the surface and it is making certain angle with the surface. If it is not normal or it is making certain angle, then there will be one component tangential to this surface. One component of the field will be tangential to the surface, and this tangential component of field will lead to the movement of charges on the surface when it is kept in the external field. But it is not so. This is not the condition in case of static charges or static conditions. Hence, we can say that the electric field is always normal to the surface. Next is, net charge in the interior of the conductor is 0, and any excess charge resides at its surface. So for this, let us again consider a conductor, and the charge Q is there on the surface. Just now we have seen that inside the conductor the field would be 0, that is E is 0 inside the conductor. And according to Gauss theorem, flux is given by E dot ds is equal to Q by epsilon 0. Since field is 0, so Q will also be 0. So third point is that the net charge in the interior of the conductor is 0, and if there is any excess charge, it will reside only on the surface. It will not remain in the interior of the conductor. Fourth point is that potential is constant within and on the surface of the conductor. Means, on the surface of the conductor, the potential at all points would be same. In other words, it will be an equipotential surface. How can we say this? We have already learned the relation between electric field and potential, which is given by E equals to minus dV by dr. This relation we have already studied, and we have learned just now that electric field inside the conductor is 0. It means E is equal to 0. If E is 0, it means dV by dr would be 0, and the differential of potential is 0. It means potential is constant. So for a conductor which is placed in an external field, the potential on the surface would be constant, or the surface would be an equipotential surface. Then next we have Fifth one, the electric field at the surface of a charged conductor is proportional to the surface charge density. Just now we have seen that all the charges remain on the surface of the conductor. There will be no charge inside the conductor when it is placed in an external field. In other words, the electric field depends on the surface charge density. Next is sixth one, the electric field is zero in the cavity of a hollow charged conductor. This we are going to see in the next video, that how can we say that electric field is zero in the cavity of hollow charged conductor. But this is a very useful application, because this is actually called electrostatic shielding, because it provides shielding to the sensitive components of electronic devices. So it saves those devices from any external disturbance by placing the metal shields around them. So now in the coming video I will be showing you how the electric field at the surface of charged conductor is proportional to the surface charge density, and how electric field is zero in the cavity of a hollow charged conductor. Thank you.